Alright, thanks for watching. And I don't want to say this video is important, but this video is super important. Especially if you're cramming for a linear algebra exam and you have one in an hour or something and you need to know all the concepts. Well, turns out this one problem has all the concepts in it, or at least most of them. So make sure to watch it. I'm not even exaggerating. So, in particular, let's take this matrix here. A is 1, 3, 2, minus 2, minus 6, minus 4, 1, 4, 0, minus 5, minus 24, 8, and 6, 20, and 1. What we'd like to talk about are what are called matrix spaces. So null space of A, column space of A, and maybe others if I have time. In particular, let's consider this matrix, and first of all, let's find a basis for the null space. Column space first. So find a basis for the column space, because it's a bit easier to find a basis for the column space. And in order to do that, let's row reduce this matrix. So you know the answer to every question in linear algebra is row reduction. So let's do that. We would like to get rid of this 3 and the 2. So let's subtract 3 times the first row from the second row, and let's subtract 2 times the first row from the third row, and then you get 1 minus 2, 1, minus 5, 6, and then let's see, 0, 0, 1, minus 9, and 2, and 0, 0, minus 2, 18, and minus 11. Alright, almost done. So we still need to get rid of this minus 2. So let's add 2 times the second row to the third row, and we get 1 minus 2, 1 minus 5, 6, 0, 0, 1, minus 9, 2, and 0, 0, 0, 0, minus 7. Okay. Again, any question of linear algebra boils down to row reducing and also finding the pivots. Notice here, there are 3 pivots, 1, 1, and minus 7. In particular, your pivots in columns 1, 3, and 5. Now, to find a basis for the column space of A, very important. Number one mistake people do in those kinds of problems, you're not allowed to choose those 3 things. You have to go back to your original matrix and pick the first, third, and 5th columns of A. And the reason for this is, turns out row reduction, they preserve linear independence. So vaguely speaking, if you row reduce, notice those 3 vectors are linearly independent. Therefore, we also get that those 3 vectors are linearly independent. So we have those 3 linearly independent vectors, and those are automatically linearly dependent. And I put quotation marks because technically a set is linearly independent or dependent, not vectors. However, row reduction destroys the span. So the span of those 3 vectors is not the same as the span of those 3 vectors. So, in particular, the basis for the column space of A is 1, 3, 2, 1, 4, 0, and 6, 20, and 1. And I totally forgot to say, what is a column space? It's just the span of the columns of your matrix. So it's the span of this vector, this vector, this vector, and this vector. But in particular, a basis for the column space is that. And question, what is this a subspace of? Well, here it's a subspace of R3. So remember, subspaces are nice spaces, and here they're subspaces of R3, and notice precisely A is a 3 by 5 matrix. So in general, it's a subspace of Rm, where A is m by n. And I like to think of it in terms of input and mouthput. So column space deals with outputs with mouthputs. Or another way to remember this, we have column space. M as in column. Okay, that's one thing. So the basis for the column space of A. Then the second thing is find what's called the rank of A. All that rank of A is just a fancy word for the dimension of the column space. How do you find the dimension? Just count the number of vectors in the basis. So here, there are 3 vectors in this basis, so the dimension is 3. That's 3, and it turns out it's exactly equal to the number of pivots here. So we have 3 pivots, so the rank is 3. And sort of the rank tells you how good a matrix is. The bigger the rank, the better the matrix. For example, the 0 matrix has rank 0. It tells you nothing. But the identity matrix has the highest rank possible. All right, so that's one thing. And then let's find, on the one hand, we found the column space. Now let's find the basis for the null space. For null of A. And again, null of A, that's just the set of solutions of AX equals 0. Which means you have to find X. Very important. The column space deals with the outputs. The null space deals with inputs. That's our yup. N. But that's good. In order to do that, well, we row reduce the matrix to the row echelon form. But to find a null space, you need to go one step further and do the reduced row echelon form. So let's start with this. So 1, 0, 0, minus 2, 0, 0, 1, 1, 0, minus 5, minus 9, 0, 6, 2, minus 7, and then we want to solve AX equals 0, so we put a bunch of zeros here. And then you want the reduced row echelon form, which first of all means the pivots have to be 1. So turn this minus 7 into a 1, and we get, maybe over there, we get, so 1, minus 2, 1, minus 5, 6, 0, 0, 0, 1, minus 9, 2, 0, and then 0, 0, 0, 0, 1, 0. Then next thing is we want to turn those numbers into 0. So the numbers above the pivots have to be 0. But that's not too bad. Let's subtract 2 times the third row from the second row and subtract 6 times the third row from the first row. And we get 1, 2, 1, minus 5, 0, 0, and 0, 0, 1, minus 9, 0, 0, and then 0, 0, 0, 0, 1, 0. Next, we want to turn this non-pivot into 0. So let's just subtract the second row from the first row, and we get 1 minus 2, 0, 4, 0, 0, and then 0, 0, 1, minus 9, 0, 0, and 0, 0, 0, 0, 1, 0. So indeed, it is in reduced row echelon form because the pivots are 1 and the stuff above and below the pivots are 0. Then, let's just solve this. So, one little thing. This will be very important in a thing I'll talk about next. There are pivots in the first 3 and 5th column. What are the free variables? they're in the non-pivot columns. So here, y and t, they're the free variables, the second and the fourth variable. And this is also very useful when you want to solve an equation. Before solving this, do that. So, then we get x minus 2y plus 4t equals 0. Z minus 9t equals 0. And the last variable equals 0. Let's call it s. And then let's solve in terms of our free variables. X is 2y minus 4t. Z is 9t. And s is 0. Okay, why are we doing this? Because again, we want to find x such that ax equals 0. So x then just becomes, again, everything x, y, z, ts. And that becomes 2y minus 4t, y, 9t, t, and 0. And you can separate out the y's. So 2y, y, 0, 0, 0, plus minus 4t, 0, 9t, t, 0. And you get y times 2, 1, 0, 0, 0, plus t times minus 4, 0, 9, 1, 0. So your null space is really the set of all linear combos of those two things. And it turns out that those things will always be a basis for your null space. So the miracle of row reduction is that row reduction automatically gives you a basis for null of A. So the basis for null of A is, in this case, 2, 1, 0, 0, 0, and minus 4, 0, 9, 1, 0. And the question is, what is this a subspace of? Well, here, it's a subspace of R5. Of R5. Well, how does 5 relate to our matrix? For A was a 3 by 5 matrix, so it's in general, it's a subspace of Rn. Rn and n as in null of A. So this is how you remember this. All right. Once we found a basis, we can find a dimension. So let's find dimension of null of A. Well, you just count the number of vectors, which is 2. Okay. Which leads us to a very important theorem in linear algebra called the rank-nullity theorem. So note what happens if you add the dimension of the null space plus the rank. Well, let's see. Rank of A plus the dimension of the null space of A. Rank was the number of pivots, which was 3. There are 3 pivots here. Plus dimension of null space, that's 2. And 3 plus 2, that's 5. How does that relate to our matrix? Well, our matrix had 5 columns. So rank of A plus the dimension of the null space equals to n. And where A is m by n. So this is always true. It's always true that dimension of the null space of A plus the rank of A equals n. And this thing, I remember it confused the hell out of me when I took linear algebra, but hopefully it won't confuse the hell out of you, because this actually makes sense. Remember, null space of A measures how bad a matrix is. It's sort of the fat of a steak matrix or something. Okay, the bigger null of A, the worse A is. Rank, which is the dimension of the column space, The column space measures how good a matrix is. So the bigger the rank of a matrix, the better. So in other words, it's the stake part of a state matrix, like it's the meat part of it. Well, if you add the null space and the column space, things should balance out. Because the null space tells you how bad a matrix is, the column space tells you how good a matrix is. And this is precisely what this is saying here. If you add the two dimensions, then you get a fixed number, which is n. Also, another way to figure this out, remember the dimension of the null space of A gives us the number of free variables. Right. The rank of A, you see, for example, here we had 3 pivots, but the free variables were in columns 2 and 4. The pivots, they give us the non-free variable, so the prisoner variables. So here it was like, columns 2 and 4 plus number of non-free variables, which were columns 1, 3, and 5. Well, if you add the number of free variables and the number of non-free variables, you get the total number of variables, which here is 5. So in fact, you see, if you add add all the columns together, so the free variables were in columns 2 and 4, the non-free ones are in 1, 3, and 5. Well, the total number, you'll see now, is just the total number of columns. That's how we do n. We don't do m because that's the number of rows. Okay, that's all I wanted to talk about here. Okay, so if you're taking my class, at least Math 3A at Irvine, this is the stuff we care about. Just in case you're taking more than that, just the row space, let me talk a little bit about the row space. So again, let's take this matrix and find a basis for the row space of A. Turns out it's even easier. So I think it was number E or something. Find a basis for row of A. Now, fortunately, I erased this matrix, but what the row space is simply you take all the rows as vectors and you take the span of it. So here, row of A would be the span of 3 minus, sorry, wrong matrix, sorry. 1 minus 2, 1 minus 5, 6. And 3 minus 6, 4 minus 24, 20. And 2 minus 4, 0, 8, 1. That's a row space. And it turns out the nice thing about the row space is, in order to find your basis, you don't need to go back to the original matrix. Just see in which rows the pivots are. Well, the pivots are in rows 1, 2, and 3. So indeed, a basis for the row space of A are simply your new vectors. So 1 minus 2, 1 minus 5, 6. 0, 0, 1 minus 9, 2. And 0, 0, 0, 0 minus 7. And here notice the row space. In this case, it's a subspace, like each vector has 5 components, so it's a subspace of R5 here, which in this case, it's n. So in general, it's a subspace of Rn. Okay. Whereas, careful, the column space was a subspace of Rm. And I don't know how to remember that, but one thing is maybe row sounds like rows like nose. That's why it's a subspace of Rn. I don't know. Okay, lastly, just then what is the dimension of row of A? Well, the nice thing is we found the number, we found a basis, just count the number in the basis, which is 3, and it turns out, incidentally, that's the same as the rank of A, because that's just the same as the number of pivots. So even though the row space and the column space are two different things, the dimensions are the same, which is a bit surprising, but I think it's pretty cool. And also, why don't you have to go back to your original matrix? Because row operations are nice with rows. They preserve span and linear independence. So it gives us an easier basis, if you like. Alright, so I hope you like this linear algebra craziness extravaganza. If you want to see more math, please click like and make sure to subscribe to my channel. And yeah, I think it's time to go.